In nearly every domain, from urban design to defense, from consumer products to medicine, value is held hostage by inertia and convention. Our mission is to challenge that. We reduce problems to their first principles and ask, what superior paradigm exists at the intersection of design, ethics, functionality, and technology? This space is built for the solvers, the engineers, scientists, and innovators who demand scientific rigor and believe better paradigms must exist. We invite your critical engagement. Contribute the data, challenge our assumptions. Your rigor can be part of the solution to the world's most stubborn problems. Come with me into the first rabbit hole. Chapter 1. Regional flights are broken. Can we fix them? Can we restore the economic viability of the regional routes that commercial aviation abandoned? Current regional turboprops, like the ATR family or Dash 8, are noisy, fuel-hungry, expensive to maintain, and can't carry containerized cargo. Short takeoff and landing versions exist, but they still demand prepared runways and heavy ground infrastructure. The solution we seek must satisfy 4 non-negotiable demands that define a superior transportation paradigm. A. Remote access. Cater to remote communities using small, unprepared airfields. B. City connectivity. Connect medium city pairs below 500 kilometers at costs lower than jets, utilizing secondary airfields. C. Silence. Beat sound curfews, enabling profitable 24-hour operations. D. Cargo capability. Transport both passengers and standardized container cargo. Chapter 2. Constraints and Antidotes. A new regional paradigm is challenged by 3 constraints. Our economic strategy is built on 3 levers designed to counteract them. A. Field and crew, the economy constraint. The roadblock. If an aircraft needs a 1,500-meter asphalt runway and a full ground crew, the economics of a regional route collapse. High minimum revenue load factors make thin routes unprofitable. The antidote: operational autonomy. Savings are derived from the aircraft's total independence. Access to secondary airfields, where fuel can be Jet A or diesel, reduces operational costs via lower airport fees and quicker turnaround times. This is reinforced by integrated stairs and a built-in cargo winch, ensuring total operational independence and minimum turnaround time. B. Mass and power, the physics constraint. The roadblock: batteries are heavy. The current energy density ceiling of about 250 watt-hours per kilogram consumes the aircraft's available maximum takeoff weight margin, crippling the payload fraction and destroying STOL competitive viability. Furthermore, the design requires approximately 7 megawatts of continuous electrical power, a currently uncertified capacity. We can't wait for the perfect battery, nor can we use a prohibitively expensive conventional engine. The antidote: constant rate optimization. The hybrid system delegates the high-power ascent to the battery bank and supercapacitors. This enables the 7-megawatt turbine generator set to operate exclusively at its peak thermal efficiency point during cruise. Cruise is the recharge cycle. This constant load operation minimizes specific fuel consumption and dramatically extends mean time between overhaul, prioritizing durability and balance in our operational costs. This is the source of the cost reduction. C. Curfew, asset utilization constraint. The roadblock: conventional aircraft noise restrictions eliminate nighttime operations, restricting profitable asset utilization. The antidote: the proposed solution creates a near monopoly that stems from 2 factors: silence and cargo. Quiet electric takeoff grants exclusive 24-hour access to airfields with noise restrictions. This design is a Combi. It can carry up to 15 LD3 standardized jet freight containers. This is a high-margin, nighttime container cargo monopoly that no conventional aircraft can touch. The passenger benefit: for a representative 300-kilometer route, the hybrid Combi STOL is projected to achieve a final fare between $100 and $140. up to $60 lower than a short-haul mainline jet. The operator benefit. The exclusive 24-hour access combined with the high-margin cargo monopoly allows for an operational utilization rate nearing 18 hours per day. We estimate this model can generate an annual net profit per aircraft of $3.5 to $5 million, outpacing the current regional average. Chapter 3. Failures of the legacy paradigm. The capability to serve small communities existed, but it failed to endure the jet age. Two core failures made legacy turboprops financially non-viable. Noise curfews. Turboprops were the first targets for nighttime noise restrictions at high-value urban airports. This eliminated the profitable middle-of-the-night cargo monopoly, drastically restricting asset utilization. Hub-and-spoke infrastructure. The economic dominance of the jet model favored long runways and expensive ground support equipment. This raised operational costs for any service using small airfields and rendered them commercially obsolete. The core lesson is that STOL capability alone is insufficient. Our solution must solve the dual problems of noise and inefficiency to remonetize underutilized short-field infrastructure. Chapter 4. Technological breakthroughs. The commercial viability of a high-performance, quiet hybrid-electric aircraft was technologically unfeasible a decade ago. The present moment is defined by increased maturity of three specific technologies. Electric propulsion, power density as the new metric to shift to electric power, is the primary enabler. High-speed, geared permanent magnet synchronous motors are achieving 13 to 17 kilowatts per kilogram in the megawatt class. This is the critical threshold that makes electric propulsion competitive with gas turbines in terms of weight. Energy generation, lightweight, modular power. The optimal architecture leverages two gas turbines, each driving a generator of the 3.5 megawatt class. This modular approach provides the 7 megawatts required and, crucially, allows the units to be switched off entirely during the noise-sensitive takeoff phase. Enforcing the cruise is the recharge cycle principle. High-power batteries and supercapacitors. Our approach is pragmatic. We select high-power density cells for the short-duration energy buffer required for ascent and backup. The supercapacitors run in parallel, acting as an asset protection system. They absorb the extreme, instantaneous electrical impulse of the STOL takeoff roll, preserving the thermal integrity and cycle life of the main battery bank. This prioritizes long-term durability over maximum range. Chapter 5. The quiet hybrid 78-passenger Combi STOL. Every design decision in this plane is dictated by the economics of the thin route. The airframe, aerodynamics, and structure. Fuselage, streamlined teardrop shape to maximize laminar flow. Its 4-meter diameter allows for 2 LD3 containers abreast. Wings, very long aspect ratio maximizes aerodynamic efficiency. The folded size is geared to fit Boeing 737 gate slots at major airports. Structural support. The wing is supported by external lift-generating wing braces. These structures are airfoils themselves, contributing to overall lift and simultaneously housing the main landing gear struts. Empennage, a V-tail design utilizing ruddervators to reduce wetted area and minimize drag. Propulsion and safety redundancy. Propulsion. The aircraft utilizes 12 electric duct fans. Lift augmentation, the Coanda effect. We utilize the powerful wash from the duct fans. This air is channeled over the wing's surface via shaped chevrons. This effect sticks the air to the wing, generating massive lift at low speeds, the critical enabler for our STOL performance. Redundancy. The high number of fans, the modular 2-generator system, and the large wing's high glide ratio, 1:20, provide multiple layers of safety margin. The batteries and supercapacitors provide an independent, immediate backup power source. Temporal advantage, door-to-door time. For sub-500 kilometer city pairs, the time advantage is significant. The hybrid Combi STOL, utilizing secondary airfields closer to the urban core, eliminates penalties like queuing and long ground transit time to primary hubs. The integrated stairs and operational independence reduce ramp time to minutes. These, however, are flights where there are alternatives. In many routes and times of the day, there is virtual monopoly. Take a regional 395-kilometer flight from Porto Alegre to Ijuí, a small city in Rio Grande do Sul state with about 88,000 inhabitants. Today, the only way to get there is by land. Using a coach bus, it takes 7 hours and costs $56. Using the proposed plane, you could land in the city's airstrip that no other commercial mid-sized regional plane could use at any time of day or night. The flight from Porto Alegre would cost $60, take about an hour. Containerized cargo could also be transported by air for the first time. Chapter 6, the military variant, the Quiet Owl. It is designed to fill the capability gap of medium-sized transport that combines high payload capacity with acoustic stealth and field autonomy. The tactical advantage, low observability and autonomy. The foundation of its stealth is the generator-off takeoff and landing protocol. By running solely on battery power, the aircraft achieves an ultra-low acoustic and infrared signature, granting a low probability of hostile detection during critical operational phases. The 1-meter rough field main wheels, high wing clearance, and integrated cargo winch system ensure the aircraft is largely self-sufficient, maximizing operational tempo from soft, unprepared landing zones. Strategic payload and mission capability. It can also carry 78 fully equipped personnel or 24-liter stretcher positions for medical evacuation. Now it's your turn. What was proposed here is just one vision of a solution to the regional commercial aviation problem. By no means it is the only one, and we're sure there are smart solutions out there. It does not matter if you're an experienced aerospace engineer or a 12-year-old kid. We want your concepts. After we reach a critical mass of a few good ideas, the concepts will be presented in a new episode and the authors credited. For that, we need two things. The conceptual design, visual a minimum of 2 conceptual drawings or renders clearly showing the concept. Hand-drawn sketches and simple digital diagrams are acceptable. We don't care about super precise or high-quality engineering drawings, although they are super welcome. We care about ingenious ideas. The technical rationale, text a technical description describing the concept's first principles, providing a credible quantitative impact, for example, estimated mass reduction, noise reduction, or time saved, and justifying its feasibility. Again, we don't care about jargon, fancy words, or diplomas. We want smart ideas. You can give an important contribution to solving the problem of resilient regional air travel. Please send your submissions to ianofwainberg@gmail.com. Until the next rabbit hole, where we will tackle a completely different problem.